Good afternoon. I welcome you to this session of fluid mechanics. Well, last class we were discussing about the discharge through an orifice. What is an orifice we just discussed, and what is the discharge through an orifice under a constant head. So let us recall a little bit of the earlier discussion. Well, if this is a tank where there is an orifice at this side, sorry, this is wrong. So this is the orifice, small hole, there is no projection, small hole, and if there is a constant head maintained, that means orifice, through orifice the water is discharged. To maintain a constant head, that means water inflow has to be there. So under a constant head means that if I consider an axis line, which is the axis of the sharp edged orifice, then this height is h under a constant height from the axis of the orifice, and if this orifice height, that means this height is much less compared to this head above the orifice, that means the height of the water surface from the axis of the orifice, then we have found out by applying the Bernoulli's equation. First of all, we see that how the streamline contracts, that is surface, we have recognized that streamlines are like this, they are contracting like this, and ultimately they come to a section very close to the orifice, downstream to the orifice, just after the orifice, section is CC, where the cross-sectional area of the stream tube is less than the cross-sectional area of this orifice. If the cross-sectional area of the orifice is A, then at CC where this stream tube converges and then becomes again parallel, this is the minimum area section, let this section is CC. After that it goes on falling because of the gravity. Then this area is AC, then AC is less than A. This is the contraction. Now if we apply the Bernoulli's equation at any point on the free surface 1 and at any point on this section CC, or at any point on a streamline, let the point may be 1 dash, let the point may be here 1 double dash, one point will be here. We will always get, after using the Bernoulli's equation, the velocity of discharge at CC of the jet, that Vc is root over 2gh. Very simple. That means we can tell this potential energy compared to point 1 is totally converted into kinetic energy, that velocity, for an ideal fluid without any loss. If we write this for this and this point, so this point is the pressure energy, because this point in the same axis, so this point and any point at this CC plane in the orifice is at the same elevation level. So therefore this is in the form of pressure energy, here the energy is in the form of pressure energy because of this height over the point up to the free surface. So this is converted to the velocity. So Vc is equal to root over 2gh. Then we found out that this is the theoretical velocity. So Vc actual, which is due to the friction of the fluid at the orifice edge, is less than this theoretical value, and this is multiplied, taken care of by a factor Cv, that is known as coefficient of velocity, whose value is less than 1, and value depends upon the height from the center of the orifice, that is the head, and the size and shape of the orifice. So therefore Q is equal to, Q actual will be equal to AC, that means the volumetric flow rate, into V actual, that means Cv into root over 2gh. Now with the definition of coefficient of contraction as the area of the vena contracta to the area of the orifice, we can write AC in terms of, let area of the orifice as AO, O suffix for orifice, C suffix for vena contracta section. Then we can write Cc into Cv into A0 root over 2gh. This we designate as a theoretical volume flow rate, Q theoretical. That means if there was no friction in the fluid, so that the total potential head or pressure head at this point is converted into kinetic head, and if there was no contraction of the streamlines, then this could have been the theoretical discharge. This is multiplied by Cc into Cv, that is the coefficient of contraction and coefficient of velocity, and this is combinedly known as coefficient of discharge. That means the theoretical discharge as defined by the orifice area multiplied by root over 2gh should be multiplied by a factor which is less than 1 to count for the actual discharge. This we discussed in the last class. Now here one thing, we assume that the orifice size is so small compared to the height above the orifice. That means if we consider a central line to the orifice, so any point on this line or any other point along the height of the orifice we will have the same liquid head H. That means with respect to this H, there is no variation of the point, there is no variation in the head of the liquid at different points of the orifice. That means any point on its axis is a representative point of the entire cross section of the orifice. So that we can tell the orifice, the entire orifice is under the head H. So that the velocity at each and every point is uniform. But it is not so in case of a large orifice. If we consider a orifice like this, consider a large orifice, that means a orifice like this, a orifice like this, very large, with respect to the head over. That means let us consider a constant head is maintained by an inflow arrangement Q. An orifice is such that we define the H1 is the height maintained, that height of the free water surface from this top part of the orifice, and from the bottom part it is H2. So H1 and H2 are different. Earlier if we define some H1, H2 from the top and the bottom, so this height is so small compared to H, so H1 and H2 are very small, very much equal. That means this height of the orifice is less, very small compared to height of the water surface from any point or any level of the orifice. But here the orifice is so large, I mean this is the height of the orifice, which is H2 minus H1. So H2 is much bigger than H1. So H1 and H2 are not very equal. That means the size of the orifice is comparable to the height of the liquid surface, free surface of the liquid above the orifice. Then comparable to H1 to H2. This is the height of the liquid. In that case what happens is very simple, a simple integration. Let us consider the orifice to be, if you see from here a view, a rectangular in shape. That means whose width is B. Then what happens? Difference is like this. If we consider an axis, you can consider, but difference is that each and every point the head of the liquid is varying. So therefore the velocity at each and every point will be changing. That means if we apply the Bernoulli's equation between a point here and a point here, we will get a velocity root over 2gh, which is where h is this height, which is varying from point to point, which starts from H1 from the upper point of the orifice and goes to H2. So therefore velocity at this point at liquid particle at here will be much higher than the liquid particle here, so there will be a non-uniform velocity distribution. So therefore what we will have to do, we will have to integrate. The simple procedure is like that. We consider an instantaneous height, that means at any level, that at any point, so let this be the height h at this point, and it has got perpendicular to this direction. If you take a view, so a small elemental strip you consider. So this is the h, all right, this is the h, and this you consider as dh. That means now you consider the discharge through a small elemental strip of the orifice, which is at a height h from the free surface. This height is h, height h from the free surface, this is the height h, and whose thickness is dh, that means whose area is bdh, a small strip, rectangular strip. Let dq is the flow rate through it. What is the formula? CD. Now we know CD into A, area of the orifice. What is the area of the orifice? bdh into root over 2gh. We apply the formula, that coefficient of discharge into area of the orifice into root over 2gh, where h is the head of the liquid. That means the height of the free water surface from the orifice. So what happens now? For this we have to find, for the entire orifice we have to integrate dq. That means what we will have to do? We will have to integrate this CD b dh root over 2gh from H1 to H2, from H1 to H2. All right. So if you carry out this integration, it will be very simple. It is equal to CD is constant. If we consider CD same at all points, it is constant throughout the orifice. B is the width, geometry of the orifice, root 2gh, it simply becomes root over h dh from H1 to H2. Simple, very simple school level things. 2/3 CD B root over 2g into H2 to the power, what is that? Half. 3/2 minus H1 to the power 3. That is the simple. Orifice is large. It may not be a rectangular orifice, depending upon its geometry, you can integrate accordingly. So this is the concept. Now another concept is that what is meant by drowned orifice. What is meant by drowned orifice? Okay. What is meant by drowned or submerged orifice. Drowned or submerged orifice. What is meant by that? Very simple. Now first let us consider a drowned orifice or submerged orifice, a small orifice. Let us consider a very small orifice compared to the head which is above the orifice. So from any point the head is h, so better we represent it from the axis. That means the height of the orifice or the area of the orifice is very small. Height of the orifice is very small compared to this height, small orifice. Drowned orifice means that orifice does not discharge into atmosphere, it discharges into another water vessel. That means other side, downstream side, there is a pressure. It is very simple. Hydraulics is very simple. This is hydraulics. That means instead of discharging into atmosphere, it is discharging into another tank where the height of the liquid, free surface of the liquid, which we call head, is h2 from its axis. Then if we write the Bernoulli's equation from 1 to 2, now this is maintained at constant h2, this is maintained at constant h1 for it. So flow will be from this tank to this tank always, but it has maintained constant because of the inflow. That arrangement do we make? That is not very much concerned that how we make it. So the height of the two tank maintained constant, h1 being more than h2, the flow takes place from this tank to this tank. So this orifice is discharging in this direction, the flow takes place this way. So now if we write the Bernoulli's equation between 1 and 2, we will get that V, the velocity of discharge for an ideal fluid, 2g h1 minus h2. Can you get it? Because you write the Bernoulli's equation, very simple. 1, Bernoulli's equation, pressure head is 0, P by rho g, taking the pressure head above the atmospheric head, then V square by 2g 0, let Z1 be the elevation head with respect to any datum, reference datum, is equal to, at this point, what is the pressure head? P by rho g, it is h2, because pressure here is h2 rho g because of this height of the liquid column. So very simple, velocity which we want to find out, V square by 2g, all in terms of the head, that means energy per unit weight, meter unit, and then rest is its Z2. Therefore V2 square is 2g, okay, into h2 Z1 plus, so V2 squared by 2g is minus h2, I am sorry, Z1 minus Z2 plus h2, minus h2, and Z1 minus Z2, that means the elevation head between these two is nothing but h1. That means ultimately you get V is equal to 2g, very simple. That means effective head causing the flow is h1 minus h2, but this is the back head. That means it is flowing under an effective head of h1 minus h2, so you will have to make it h1. But in this case, one interesting thing is that there is no difference between a large and a small orifice. Thing is that if we have a large orifice, for example, this is a large orifice, this is a large orifice, and let this side also, this is a large orifice, let this h1, and this side let this is h1 dash. There is no difference between large and, why? How? I show you. Let this is h2, that height of the water level from the bottom in this side, and correspondingly this side h2 dash. So entire orifice is under an effective head of h1 minus h1 dash. Can you recognize it? Because this large orifice can be considered similar as a small orifice under a effective head h1 minus h1 dash. Why? Because here what happens, when the head varies point to point, then whatever is added from this side is also added from this side. For example, at this point, what is the effective head causing the flow? h1 minus h1 dash. What is the effective head causing the flow? h2 minus h2 dash, that is h1 minus h1 dash. At any point, the effective head causing the flow, let this is h, and if this is h dash, then the effective head causing the flow at this point is h minus h dash, which is nothing but h1 minus h1 dash. That means any increase in head from this side favoring the flow is same way obstructed by the same increase in head in this side. So therefore, for a drowned orifice, a large orifice whose height is comparable to the head of the liquids above it can be treated as a small orifice under a drowned condition or under an effective head which is h1 minus h1 dash. That means difference of the water level from its upper point. Clear? Alright. So this is a trick, that if there is a large orifice and it is a drowned or submerged orifice, it behaves as, that means the velocity through this is theoretical case is root over 2g h1 minus h1 dash. When there was no downward orifice, then the difference in head counted, because downstream side head is uniform, that is atmospheric pressure. Here the same head is added. Okay, it's very simple. Drowned or submerged orifice. Now we will come to time of emptying tank. Time of emptying a tank is an unsteady problem. So far we have discussed the discharge with a constant head, but if head is not maintained constant, and there is, for example, consider a orifice at the bottom of a tank centrally, and if the initial head is H1, let us come, this is a transient problem, unsteady problem. That means we do not have any provision for inflow to maintain this head constant. So what will happen? The streamlines like this, let me draw this. That means what will happen? The water will be drained out through the orifice, coming out. So head will be decreased. So the problem is posed like that. What time will take for the head to come from H1 to H2? Let's example, what is the time taken? This type of problem. So it is very simple. So this orifice is under a varying head. Therefore the discharge is maximum when the height above the orifice is maximum. That means at initial level. Then as the height falls, the discharge rate is reduced. Let us consider any instantaneous height h above the orifice, this bottom plane h. So in that case, the discharge through the orifice, that means Q discharge through the orifice, Q is what? Let dq, small discharge to the orifice is CD into orifice area is A0 into root over 2gh. CD takes care of all the losses, frictional losses and contraction and all these things. So if we consider dh is the decrease in the height, now this is the dh is the decrease in height for a time t, or rather we can think in various ways. We can consider that if F is the cross-sectional area of the tank, the rate at which the volume flow rate is reduced in the tank is A dh dt, and that must be equal to CD A0 root over 2gh with a negative sign. Why? Because h is decreasing with time. That means A dh dt is the rate at which the volume is decreasing in the tank, the volume flow rate is decreasing. That means it can be conceived this way, that during a given interval of time dt, the head has fallen, the height has fallen by dh. So therefore the volume, this has been decreased, is minus ADH, and this must be equal to the flow which has gone through the orifice, the 50 years back explanation dt. So ultimately ADH dt, but you should write straight in terms of the rate. The rate of volume flow in the tank is ADH dt in terms of the instantaneous height of the tank, and rate of the volume flow through the orifice is equal these two rates under continuity equation. So therefore it becomes simply dh dt is minus CD A0 root over 2g, all the constant together, into root h dh dt is equal to minus. So we can find out time like this, dt is equal to, so dt is equal to, this will be like this, A by CD A0 root over 2g into h to the power minus half dh with a negative sign. With a negative sign, but with a negative sign. Now the time taken for the height to come from h1 to h2 can be written as by integrating dt is equal to, let that time is t, then you just integrate this, these are the constant, a CD A0 root over 2g integrate h to the power minus half dh. Now from a initial height h1 to h2, so it should be h1 to h2, I take care of the minus sign, so I write h2 to h1. That means if we integrate it, this time taken will be simply a by CD A0 root over 2g. Now this integration will be what? 2 minus half plus 1 half 2 and h1 to the power half minus. So this is precisely very simple. Now if one has to find out the time of emptying, which I started. Time of emptying means H2 is 0. So starting from an initial height H1, the time of emptying the tank will be this multiplied by H1 to the power half. But here one thing is very simple. The tank height, a tank area is constant or uniform, it doesn't vary with age. So integration becomes simple. There may be a tank of some geometry where the area may be a function of age. So there is no fluid mechanics. It is simply school level integration. That means there may be an orifice in a prismatic tank like that. Difference is that here the area, that means at different head the area is changing. That means if you start with, let this is the H1, the same problem if you pose the time of emptying or reducing the height from H1 to H2, whatever it is. So same problem if you pose at any instantaneous height H from this, if you consider the area of the tank there, that means okay, the through orifice the flow is same, dq is rate of flow is CD into the orifice area is same root over 2gh. But the rate of volume flow rate at this level is minus A, which is a function of H. A is changing, AH dH dt, which has to be made equal to CD A0 root over 2gh. That means you will have to take dt in one side and dH. So A as a function of H only you have to incorporate. There is no fluid mechanism. This you can find depending upon the geometry. If this is a prismatic tan, say straight surface from the inclination, something will be given in the problem so that from the geometry you can express the area at this section as a function of H and can integrate it. There are several problems, standard problems. One standard problem is solved in my book. There is a hemispherical. There is a hemispherical vessel and there is a, this is the hemispherical vessel, let it is upper surface, this is the center of curvature for this hemisphere, hemispherical vessel, the fluid is coming out. So it starts with some H1 and then it goes to another H2, goes to another H2. What is the time taken? Very simple, at any instant you consider this as H. So CD A0, this orifice area is A0 root over 2gh. This must be equal to the area here, that means an elemental area here, which is A as a function of H minus AH dH dt. Now we have to find out H. For a hemisphere it is very simple. If this is H, already I have done it. So therefore this is a circular cross section. So this area will be, if I define this as x, this is equal to pi x square. And this x from the geometry, see this is the radius of the hemisphere which will be given, the geometry of the tank, and this part is r minus h. This is also r because of it is a hemisphere. So this is equal to pi into r square minus r minus h whole square. So you can find out x as a function of h, r is constant. So therefore h as a function of h, you put it and then take t at the one side dt and integrate this function of h from h1 to h2. Take care of the sign and get the answer. That's all. So this is the unsteady problem. That means when the orifice is discharging under a varying head, which is the practical problem of emptying a tank. That means the water level in the tank falls down as the orifice is placed or orifice is opened. All right. Now last part I will discuss the mouthpiece. What is a mouthpiece? Mouthpiece. Now it has been found that by attaching a short length of pipe, cylindrical length of pipe at the side instead of an orifice, a short length, the discharge is enhanced as compared to an orifice. That means if there was an orifice, sharp project orifice, what could have been the discharge? The discharge will be more if instead of the orifice, if we attach a short projected part, short of a cylindrical cross section, very short, which is known as mouthpiece. What is the physical mechanism for it? Why the discharge is increased? What happens is that this contraction which takes place is again filled up. So therefore, when the discharge is taking place, then it is full flow. Let the area A0 is same as the orifice. If we consider an orifice, what could have happened in case of an orifice? If there was an orifice, this area could have been just like that. I just show you. If there could have been orifice, what could have happened? This. So therefore, the area AC gets reduced from this A0. So therefore, the reduction of area or contraction is not taking place. It expands the tube and then finally flows. So therefore, there is a possibility of enhancing the head, enhancing the discharge Q. But there is a question. Let us consider a short height, that is the head or the height of the free water surface is same for all points, and we take a representation as the axis. Now the question is that, okay, I understand here contraction is there, here also contraction takes place, but this is again refilling the tube, a short portion is there, so that when it comes out it is fully filling the A0. That means the effective flow area is A0, where here effective flow area is AC, which is less than the A0, AC is less than the A0. And the way we define the coefficient of contraction, CC as AC by A0. But at the same time, due to contraction, there is some loss. If I consider this short section, so that the friction we neglect, then at this, but we cannot neglect the losses due to contraction, which we have discussed. This is the contracted area CC. So whether the loss counterweighs the discharge rate or not, let us see. And it has been found, it can be proved theoretically that discharge rate is enhanced by refilling the liquid in the tube. That means to increase or expand the stream tube so that the effective flow area becomes the total area of the mouthpiece A0, even if there is a contraction loss. Okay, let us see. Now this is the section let this is the section 1, and we write the Bernoulli's equation. Let us write the Bernoulli's equation. Here pressure head is 0. Atmospheric pressure we take 0. Let us now consider unnecessary Z1, Z2. This axis is the datum. So velocity is 0, H. H is this. Now at 2, pressure head is 0, atmospheric discharge, and this is the velocity which we are finding out. Now let us forget about the friction. First of all, friction part we neglect, and it is a short tube. When you will compare with an orifice, we will consider frictionless orifice also. So that don't worry, comparison will be at the same basis. But loss, this loss you have to consider HL, that losses due to contraction. So therefore you see V2 square by 2G is equal to H minus HL. All right. So what is HL? Now you tell me, what is HL? So 0 plus V2 square by 2G plus HL. What is HL? If you recall, HL is, it is due to the contraction. Actually the contraction loss is due to the expansion itself. I told it repeatedly, and this is nothing but Vc minus V2 whole square by 2G. We have deduced it earlier that it is the loss due to expansion, not due to contraction. After contraction, when the stream tube expands, so it is just the loss due to expansion of the stream tube. That means Vc minus V2 by 2G whole square. That means if I take this V2 square by 2G common, then it is Vc by V2 minus 1 whole square. Now Vc by V2, if you see here, the continuity equation, Vc into Cc is equal to V2 into A0, the continuity between these two sections. Therefore Vc by V2 is what? A0 by AC. That means 1 by Cc. Cc definition is AC by A0. That means we can write HL is equal to V2 square by 2G 1 by Cc minus 1 whole square. So therefore, if we place this here, what we get, if we place H2 here, that means it goes this side. Therefore V2 square by 2G into 1 minus 1 by Cc minus 1 whole square. I take this here, HL plus, very good, plus is equal to H. Okay, this is okay. Now I write here, therefore V2 is equal to, now if I take this as K, which is very important. What is K? K is equal to 1 plus 1 by Cc minus 1 whole square. This is K. That means this coefficient of V2 square by 2G. That V2 is root over 2GH. Okay? Then what is the discharge Q? Area is A0. Here area is full A0. There is no contraction. A0 into, oh God, divided by under root K. I am sorry. So Q0 into root over 2GH by under root K. That means we can tell that CD for mouthpiece is 1 by root over K. This acts as the CD for mouthpiece into A0 root over 2GH. This is the mouthpiece, QM. Now what is the Q for, leave it. What is the Q for orifice? Q for orifice is CD into root over 2G under the same head. Now CD we can write as CC only. Why? Because here also I want to neglect the friction. That means CD is equal to CC into CV. We make CV is equal to 1. Fluid friction we neglect. But contraction is there, so CD is equal to CC. So therefore here CD is equal to CC. Now if I can prove that 1 by root K is greater than CC under all conditions, then I can prove that mouthpiece always enhances the flow rate. This can be proved. This is a simple school level mathematics, that for values of CC less than 1, 1 by root K is greater than CC, or 1 by K square is greater than CC square. Okay, you see that this can be always proved, or you can prove that other way, K square, this one K square is less than K, sorry. Then we can write K is less than 1 by CC square. All right. So provided I can prove 1 by root K is greater than CC, and 1 by root K is always greater than CC for small values of CC. How can it prove? How can you prove it? Let us prove like that. This is the K. Let us reform it in this way. 1 by root K is greater than CC. I will have to prove. That means I will have to prove K is less than 1 by CC square. K is less than 1 by CC square. One line proof. You just break it. 1, then plus 1 minus 2 by CC, all right, plus 1 by CC square. 2 minus 2 by CC. 2 by CC is greater than 2. 2 minus 2 by CC means this is a negative. So 1 by CC square minus something. So K is less than 1 by CC square. Very simple. One line proof. Because for all values of CC less than 1, because 2 by CC is greater than 2, 2 minus 2 by CC plus 1 by CC square. So therefore K is always less than 1 by CC square. So this proof is not given in my book, but I have written exclusively that for all values of CC less than 1, this one. So this is proof that mouthpiece enhances the, the discharge rate. Any question, please? I think this is so simple that it. Now, one dangerous thing is there. Can you tell me what is the dangerous thing? Now here you see, whenever there is a contraction, that means here the velocity, if you compare V2 and VC, VC is greater than V2 because AC is smaller than A0. So therefore PC is less than P2. And what is P2? P2 is atmospheric pressure. That means if there is an atmospheric pressure discharge, and if there is a area where in the upstream where the pressure is lower, or there is an smaller area in the upstream where the velocity is higher than the discharge velocity, there is a chance that the pressure will be, chance means obviously there is a pressure will be lower than the atmospheric pressure. So therefore it is proved qualitatively or physically that the pressure at the vena contracta is lower than the atmospheric pressure. So we can find out this vena contracta pressure by applying the Bernoulli's equation either between point 1 and 2 or between this point C1 and let a point C here, between point 1 and C or between point C and 2. All right, let us write the point 1 and C. You write 0 plus H is equal to what? The point is under question is PC by rho G plus VC square by 2G. All right, so PC by rho G is equal to, but I think this will not help. We want to find out how much it is less than the atmospheric pressure. So therefore you write between these 2 points. So forget it. So you write PC by rho G plus velocity head Vc square by 2G plus, let this line is the datum line 0, and you equate it with the 2 at any point in this section. This will be the atmospheric pressure. Let I write the P atmospheric, that means PC I express in the absolute rho G plus V2 square by 2G plus HL. Well, If we do so, then you can write Pc by rho g is equal to P atmosphere by rho g minus V2 square by 2g minus Vc square by 2g minus HL. Now this can be written as P atmosphere by, in terms of Cc only. So very simple, you just take HL. Now this I can write V2 square by 2g minus V2 square by P atmospheric pressure plus V2 square, very good, minus plus V2 square minus Vc square by plus HL, very good. So Pc by rho g is P atmospheric by rho g minus Vc square by 2g, V2 square by 2g plus HL, very good. So now minus V2 square by 2g, 1 plus V2 square by 2g, 1 minus Vc by V2, okay, whole square, all right, plus HL. What is H? Now this can be written as P atmosphere by rho g minus, this is the discharge, what is Vc by V2? Again Vc into AC is equal to A0 into V2. So Vc by V2 is 1 by Cc. So 1 minus 1 by Cc square, 1 by Cc, Vc by V2, okay? Plus what is HL? HL, why not we see here? V2 square by 2g. Huh? What happened? All right, all right. Very good. Cc minus whole square. Okay. All right. Now I can write Pc by rho g all plus P atmosphere by rho g कर दो माइनस V2 स्क्वायर बाई 2g, क्या करेगा? दिस माइनस करके 1 बाई Cc स्क्वायर माइनस 1 एंड प्लस 1 माइनस 1 बाई Cc. ऑल राइट? ओ 1 बाई Cc माइनस 1 होल स्क्वायर. This is V2 square by 2g minus, so I have taken the minus, so it will be minus. I am sorry, minus 1 by Cc whole square. So now this can be also told, also shown that it is positive quantity, so that this is always less than P atmospheric by rho g. That I leave you as an exercise that I have shown for all values Cc less than 1, this is a positive quantity. Now I tell you a representative value, if you take Cc is equal to 0.62, then you get the value of K, this one. If I come to this value, that here if you see that root over 2gh, where I deduce the earlier one, V2 is, yes. So root over 2gh by root over k, the value of k, if you recall the value of k, this is the value of k, 1 plus 1 by Cc minus 1 whole square, with the value of Cc is equal to 0.62, the value of k is 1.375. So CD, which is 1 by root over k for mouthpiece, become 0.855. And CD for orifice is Cc, that is 0.62. Very important thing. And if you put that value 0.62, here you get, this is a representative value. Cc usually lies between 0.6 to 0.65. So minus 1.225, roughly the value is like that. That means this will be lower than the atmospheric pressure by 1.225 times the discharge velocity here. So therefore we see by attaching a mouthpiece, that means a short portion, cylindrical portion, short portion, so the discharge rate will be increased. But thing is that why I am telling a short portion, if instead of that we give a very long cylindrical part projected, discharge rate may not be increased. Why? This is because frictional loss will be more. That means apart from this contraction loss, there may be more frictional loss, so that the actual velocity of discharge will be much less than root over 2gh plus all those. So this HL will increase much. That's why a short, because short range orifice friction is very less. CV value usually lies between 0.9 to 0.95. So therefore, we must have a very short piece which is just sufficient to expand this stream tube. All right. So this is a very important statement. Sometimes it is written in the book, a short portion. What is the meaning of the short portion? Because in the field of science, the words used are not redundant. There is no use, there is no scope of using more adjectives and all this things. So each and every word has got its implication. So today, yes, I conclude this talk. So we have completed the application of Bernoulli's equation. If we look back at the beginning, we have first recognized the Bernoulli's equation, that is the pressure head plus the velocity head plus the kinetic head plus the datum head, the potential head, and the three components of mechanical energy remain constant everywhere in the flow field, provided the flow field is irrotational. But for a rotational flow field, it is constant only along a streamline. Then after that, we recognize the solid body rotation, that is the force vortex, what is a free vortex and irrotational vortex, pressure distributions in force vortex and a free vortex. Then we recognized the different losses, siphon, then probably siphon, we studied siphon, what is the principle of siphon, how the siphon works, then different minor losses, losses due to expansion, contraction, then the concept of static pressure, stagnation pressure, pitot tube, application of pitot tube, then the discharge through orifice and mouthpiece. This we discussed. So today I conclude this chapter. Tomorrow, next class, I will start the incompressible viscous flow. Thank you.